Yeah, good afternoon, ladies and gentlemen. What I've done is construct paleogeographic maps for the Gulf of Panama in a very simple technique using bathymetric maps. So using the seabed contours and then relating those to sea level curves to give us time of different depths. I'll show you two sets of charts, two sets of maps, paleogeographic maps. The first one is for the whole of the Gulf of Panama based on a British Admiralty chart. It's the most complete one that I can find, and it's based on US Navy surveys from the 1970s. And then there are a more detailed series of maps from the Instituto Geográfico Tomé Guardia, based on their 1 to 50,000 scale topographic maps. And those maps, the ones for the Pearl Islands, have detailed bathymetric data, soundings data, carried out by the US Navy in the late 1920s, early 1930s. As I said, what I did then was digitize the contours on these maps and then relate those contours to the time using sea level curves. Now, there are a number of uncertainties. Basically, for a particular depth, say 100 meters, you can give it a certain time, but there are variations between sea level curves, and there's quite a large 2 sigma error on a lot of the data that's been used to construct sea level curves. There's no sea level data from the Gulf of Panama itself. That is something that's lacking. So we're using data, worldwide data from other sources to correlate this. And finally, that this does not account for any post-transgression sediments, so that these are, in some cases, particularly in the inner part of the Gulf where there's more sedimentation, these are minimum ages. In other words, for a given depth, the age that the sea actually arrived at that part was probably a bit older than the date that we get from the seabed, because the actual original surface was a few meters below that. This is first of all a word about datums. This is a tide. What I've plotted up here is a tide chart for Balboa for the month of April. You can see the extreme tidal range in the Gulf of Panama up to a maximum of, in this month, 6.25 meters. And to illustrate, the land and bathymetric charts use different datums, different zero levels. On land, you use mean sea level, which is, as you can see, is the average, more or less, of the tidal range. And most, I think all sea level curves use this as their reference point as well. Most papers, unfortunately, don't actually specify what datum they use, which is an oversight, but the ones that do state that indicate that it is mean sea level. On the other hand, for bathymetric maps, their zero datum is mean low water springs or chart datum. And in the case of the Gulf of Panama, this is considerably lower than mean sea level, 2.56 meters. It's measured precisely by the Canal Authority at the port of Balboa. So other parts of the world, it's usually a lot less, but because of the extreme tidal variation here, there's a large difference between the two. This is set very low because obviously a ship's captain wants to know the minimum depth of water he's got beneath him, not this depth. So what I've had to do is make an adjustment for the curves by adding on this 2.56 meters to the curves, as I do to the times. These are the types of sea level curves. This is from Flemington 98. And they show from the last glacial maximum at about 21,000 years ago, as the glaciers in the northern hemisphere and the southern hemisphere started to melt, sea level started to rise. At the last glacial maximum, sea level reached somewhere between 120 and 130 meters below present sea level, below present surface. And there was a rapid rise, more or less straight, with some influxions with meltwater pulses from large dammed up lakes. There was a rapid rise up until between 6 and 7 million years, 6 and 7,000 years ago. As a geologist, more used to talking billions of years. To about 6 or 7,000 years ago, and then the last 6 to 7,000 years, the last 2 or 3 meter rise has been very gradual. You can see the 2 sigma error bars of the data are plotted on this. You can see this quite, say for a particular depth in here at say that would be minus 70, you can see it's quite a range of values over 1 to 2,000 years. So in all these cases, the dates are plus or minus at least 500 years. And finally, the other aspect about sediments. This is a map of seabed sediments from Golik, 1968, in the Gulf of Panama. On the outer part of the shelf, the grey texture is sand and shell deposits, and they represent beach deposits or near or shallow water deposits. So they actually formed as the transgression. These are transgression sediments. They actually formed as the water rose and covered this. So these do represent the original pre-transgression surface. This hatch pattern is clay muds, and these are recent sediments, post-transgression sediments. They're only in the inner part of the Gulf because they're derived from rivers and from runoff, and only reach a depth of about 70 to 80 metres current depth. So for the curves, for the younger part of it, closer to shore, then these we're looking at minimum ages. There are these can have depths of up to 20 metres, these sediments, but unfortunately there's not enough information from seismic lines or surveys to be able to plot. There's just one or two lines, but there's not enough information to be able to correct the curves for this. This would need seismic data on a regular spacing to build up a detailed profile of the depth of Holocene post-transgression sediments. But for the main part of our story that we're interested in, the deeper parts of the shelf and the areas around the Pearl Islands are mostly transgression sand or even bedrock. So the dates that we're getting from the depth of the depth of the seabed are probably close to the ages of the transgression. What we'll go through now is a series of maps at 10-metre intervals. This is for the whole of the Gulf of Panama, and this was at the last glacial maximum about 21,000 years ago, when the sea level reached a depth of about 120 to 130 metres. And you can see that the Gulf of Panama was a large, flat, dry plain extending all the way from Punta Mala all the way to Punta Pina, the Tropic Star Lodge, about 200 kilometres wide and 150 extending for about 150 kilometres from Panama City. It was probably a savanna grassland based on palynology from cores in lakes at Value. There's a drier climate, and so it's probably a very extensive grassland, very, very flat lying. The Pearl Islands would have formed a range of low hills, and there would have been some small steep hills in the Taboga group of islands in Otoke Bona. They would have been short, they'd have been small steep hills, rather like Cerro Ancon is today, with flat land around them. So we'll go through these quickly. You'll see how the sea level starts to rise. I've shaded it in different colours of blue. And when we get to about 14,000 years ago, this was when the first human migrations through the isthmus started, going from North America to South America, and they would have seen a very different landscape from today. The plain was still very extensive, there were no islands yet, and it is likely that if they followed the coast and their migratory routes, then it's likely that any archaeological sites are now underwater. There are no known sites of this age in Panama. And we can see that similar happens. Now we're starting to form, by about 10,000 years ago, the Pearl Islands are starting to form a peninsula, but they're still connected to the mainland. And then by about, the Pearl Islands become one big island at about 9,200 years ago. Then the next thing is they separate into three islands. You have a big island, Isla del Rey, extending all the way up to Pacheco, and then Pedro Gonzalez and San Jose have separated into separate islands. They were probably joined initially. Probably there were two islands first, and then these two separated into individual islands. And then over the last few thousand years, the gradual final rise of sea level, these islands, the northern islands, which are separated into individual islands, Contador and so on, they're all naturally separated by very shallow water, just in the order of 5 to 8 metres depth. Now we move on to, these are the detailed maps of the Pearl Islands based on the topographic maps from the Instituto Geográfico Nacional. You can see that the data's, the profile over here is particular, is a bit different. It's showing a wider channel here. So there's differences between different data sets we have to take into account as well, and another source of uncertainty. But we see here at These depths on these maps are in uneven numbers because, first of all, the maps, the bathymetry was produced in fathoms of 6 feet, and then converted that to meters, and then added a conversion to bring it to the same datum as the land. So that's why the numbers are rather uneven. So at 57 meters between about 11,500 years, it's still a peninsula in the Pearl Islands. Over the next 1,000 years, by the time we get to the next contour, 39 meters, it's now formed one big island, and you can see there's now a considerable channel separating that from the mainland of Darien. In the order of, these are 10 kilometre squares. It's in the order of 10 to 15 kilometres separating that. This is, now we've got, by about 8,500 years, the Pearl Islands have separated into 3 islands. You can see one big island over 50 kilometres long, extending from Pacheco to Isla del Rey. Pedro Gonzalez is a separate island, and San Jose. And then the final rise of sea level, the smaller islands start to separate. And this is around the time slightly before the date of the archaeological site on Pedro Gonzalez, which is located here. So by the time of that site, the islands had already formed, they'd already been separated as islands, and were separated by a considerable distance, almost more or less the current distance from the mainland. So one of the implications of this is that those inhabitants used seaborne transport over considerable distances to migrate and to get to and from the islands. Now we want to say a little bit about the geology, because the geological setting of this is important for the archaeological site. This is a view taken from a commercial flight, one of the Copa flights coming into Panama. It's a bit hazy because it wasn't through the window, it's not a great day. But looking west, this is the Don Bernardo beach where the archaeological site is that Richard will talk about. And I've looked at the geology around this area. This is, go back first of all, the geology of the Pearl Islands is very poorly known. This is the best geological map there is on a regional scale. Pedro Gonzalez is shown simply as a Eocene basal conglomerate, which there's no conglomerate there, so not sure what that is. Tony Coates took the same map and named the different formations with the type localities and the Darien. But again, this is Pedro Gonzalez with a big question mark, possibly correlated with the Darien formation of Eocene or Oligocene age. But what we see on the island doesn't match any of the type sections or stratigraphic sections that are described in Tony's paper. So this needs to be mapped geologically and properly located within the stratigraphy and work done on the sediments to determine the age of them and on the volcanic rocks. So provisional site at Eocene or Oligocene age, but with a big question mark. What we actually see on the islands, this is on the point at the beach, are an interbedded sequence of basalt lavas and well-bedded sediments, fine sandstones. And these white spots that you see in the lavas are geodes or nodules of agate, which was the raw material that was used at this site. Take a closer look at that flow now, looking at the profile of the flow. We can see in the lower part it's massive basalt. There are no pillow textures here, so it may not have formed on the ocean floor. It may have been more shallow water or subaerial. You see the top part of it is full of these white nodules, and these formed as gas bubbles in the lava flow, in the upper part of the lava flow where it's frothy, almost like an aerobar, and then subsequently low temperature hydrothermal fluids came along and deposited silicate in these, forming these nodules of agate, and also in fractures. You can see some here, white fractures with agate in them. One of the remarkable things about this is the size of these agate nodules. This is a pen for scale, so you can see these nodules are fist size or size of grapefruit. Some of these are very unusual. I've never seen agate geodes this big. Normally they're very small, like this, the size of a pea or a lentil or something. They're normally just a few millimeters in most places that you see basalts like this. So it's very unusual to get these. And when we see on the surface, I think this was one of the reasons that this archaeological site was here, because they were using this as raw material for making a lot of the vast abundance of tools made from agates on these middens. That's a photograph taken just on the surface of one of the